So I'd like to begin by saying I'm tremendously honored to receive the Harvey Prize. I don't know if there's a representative of the Harvey family here, but I'd like to say thank you if there is. The Harvey Foundation, I'd like to thank them. The Technion for organizing all this. It's really wonderful. It's a great experience for me. I had the chance to bring my wife with me to Israel this time, and it's a great experience for her as well. I'm asked to spend about 15 minutes to tell you a little bit about Attosecond science. And I had planned before Professor Levine's long introduction about what an attosecond was to start out directly with what an attosecond is. But I think you've all heard now, and everybody knows, it's really, 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 really short. The University of Ottawa had a publicity campaign about 2 years ago, and they chose a few ideas for the publicity campaign, and they went to some photographers in Ottawa and asked them to take some picture that captured the essence of what it was. So I used that as my introductory picture. You can see it up there. It has me catching, well, it's really a ball. I was holding a ball in my hand. But it's supposed to be catching an electron, and they called it catching electrons. I was a little uncomfortable about this advertisement because, you know, being a physicist, I know an electron isn't really a ball. However, I thought perhaps it captured the essence of the subject. It's about controlling, manipulating, measuring, and in the sense of photographing, perhaps catching an electron. So I let the go through, and I like the image. So there were two students, and I wrote what happened to them. I won't say any more about them. So let me begin by saying, if you imagine going out to a lake and taking a rock and a pebble and throwing it in, you will see a wave that's formed immediately, and the wave is really short. It's really one oscillation of the water wave. That's not so much different than what we try to do with light waves. Light's a wave like a water wave, and we try to do something very similar. Actually, if you look at the water wave picture that you see there on my left, your right, I guess, on your right, you will see that after it's moved away a little bit from where you threw in the rock, out to the outside is long wavelength light, and as you move in towards the center, the wavelength gets shorter and shorter. In fact, that tells you that to make a short pulse that's only basically an oscillation wide, you need many wavelengths of waves. In that case, water waves, but it's no difference at all with light waves. So in order to make a short pulse of light, you need many waves, and you see on the right an image of, in that case, 7 different waves, all of slightly different wavelengths, and all just exactly synchronized together so that right in the center of that image, every peak lines up, making a larger peak at the center, and as you move off to either side, left or right, the peaks are shorter. And that's how you make a short light pulse. You get a whole set of waves of light, and you add them together, perfectly synchronized as seen here. Well, you can imagine that lasers had a great deal to do with making very short pulses of light because lasers are all about controlling light. With the discovery of the laser in 1960 and immediately afterwards, we learned how to make short pulses of light. It's actually shown there on the image. In 1964, when it was really discovered how to synchronize many waves, as I described to you before, and from then on, we made shorter and shorter pulses of light for about 20 years, till about 1986, going not down to attoseconds yet, but starting at picoseconds, and it allowed us to measure many, many fast phenomena in nature. Things like what happens in a semiconductor when we try to run a current through it to make faster devices, for example. And what happens in a molecule as a molecule begins to come apart, and can we see it coming apart? But that process came to an end when we, with ordinary laser light, the light that can be made with a laser, when we came to sort of the limit. We couldn't make any more wavelengths synchronized, and the wavelength anyway was kind of long. And so what I'm going to talk about then is what did we do next? And that's why I'm here. What did we do next? On the right, you can see the timeline of what we did next, but I'm going to show you what we did next in an illustration. So on this illustration, how to make an attosecond pulse, you see in yellow, I hope you can see it in yellow, and the computer in front of me, I can see it, but I don't know what you can see. You can see a wave. It's almost like a water wave, but it's really light. Light as a wave. It's a light wave. It's quite an intense wave, but you can't quite tell that from the figure. And in the figure, there are 4 images of an atom. There are really 4 snapshots of the atom in this illustration. On the left hand, or my left hand, your right hand snapshot, on the right hand snapshot, you see the atom in the middle of the peak of the wave. The wave pulls at the electron. Remember, this is all about electrons. The wave pulls at the electron, and, well, if it's strong enough, it can pull it away from the atom. So there you can see it on that figure being pulled away from the atom. Of course, the wave moves, and pretty soon the peak of the wave, the crest of the wave, has gone by, and we're down to the 0 part of the wave. But by that time, the electron has gained a lot of momentum. You can think about this, not much different than a cork on a water wave. It's bobbing up, and then it stops, and it's going to bob back down again, and as the wave turns its direction, it turns around, and it comes back. And when it comes back, it can bang into the ion from which it left. You can hear the noise? That's the flash of light. It gives off a flash of light. But the flash of light is really well organized. If it happens a little bit later, it comes back early, and it makes kind of reddish light. It's not red, it's actually ultraviolet, but I show it red. If it's born a little earlier, it comes back a little later, and it makes, well, I was supposed to be green, but it's brown on my screen. Brownish light, and it's really ultraviolet, quite ultraviolet. And if it comes back at the optimum time, it bangs the hardest, makes the shortest wavelength of light, and there are all the colors we need to make an attosecond pulse right there. Huge, huge, huge bandwidth, all perfectly synchronized by their motion in this electric field. This electron that comes back can do other things as well. This electron can pay pool with the other electrons, knocking another one free. But that's not mostly what attosecond science is about. But there is an element of it that's about this playing pool or knocking another electron free. Or it can scatter. That is, think of a wave coming and having a couple of rocks and how the waves would diffract off these rocks and the ripples that would be made in a water wave. I'm going to mention that just briefly again, but the thing to mainly concentrate are the different colors of the light that's produced and how well they're synchronized, and that's the attosecond pulse. So actually this is, I just sort of mentioned it, it's 4 advances of 1. It's a way to go from femtoseconds to attoseconds. It's a different kind of way to think about how light interacts with matter. It's called nonlinear optics, but you can ignore that. It's a way to extend light, laser-like light to X-rays or to soft X-rays. And, well, it's a collision physics thing because it's about colliding. So that's 4 advances in 1, really. Well, of course, the wave I showed you, maybe we couldn't quite make out of a laser. We can do something not so far away from it. I can see Eugene Frimker down there smiling at this because he made up this view graph a number of years ago. It might not just be one wave, maybe it's more than one wave driving it, in which case, well, the electron can come back once or twice. Now that sounds kind of funny, because one electron, if it came out, it would come back and hit, and where's the other electron? Quantum mechanics is a little bit different. It allows you to take a little bit of an electron out once, and then a little bit more of it out again. I'm going to say a little more about that. So you have to suspend your judgment of this wave and particle, and remember that physics is kind of bizarre in this way, and it allows for more than one. And if it happens more than one time, it gives a set of frequencies, a whole comb of frequencies, that can go up into the soft X-rays. So it's really an interesting phenomenon. The whole process is not so complicated. This is what it would look like where the vacuum chamber, which is sort of implied here, is taken away. You've got a beam of light coming in from a laser out here, on my right, on your left, I guess. Coming in, it hits a lens. It's focused into, well, you can see this thing coming down from the top. That's a jet of gas shot into the vacuum, and then the beam of this new color of light, this attosecond pulse, is sent off where we make a measurement of it. And measurements are shown on the bottom. So for the first time, we have the time resolution to observe electronic events in atoms, molecules, and solids on their natural timescale. Again, we heard that from Professor Levine to start with. But those of you who are physicists or who like to read about physics or quantum mechanics and all the bizarre parts are going to say, where is the quantum mechanics in all of this? So now I want to take the same perspective that I did before. So if you think it's complicated, it's only the wave and the particles, but said in a different language. And I want to give you that different language and give you a different perspective on it. Now, if there are any physicists in the audience, they can look at the stuff at the very top. The rest of you don't have to look at it. But shown there on the figure is the, well, something like the atom I had before. That's holding the electron. Now, there's no particle that you saw before, but really the reality of the world says that it's not really an electron, it's not a particle. It's a wave-like thing. And so that peak you see on top of the hole is what the wave might look like if it were just a hydrogen atom and there were a single electron there. And that's what it looks like. And so now when the field is there, it pulls the electron out, but it's not a particle that comes out, it's a wave that comes out. And you see the wave moving off to my right, to your left. And, well, it's hard to illustrate what a wave does without a movie, and I didn't want to bring a movie. So you can have to imagine that electron spreading out and coming back, and as a wave, it collides. And when it collides, it overlaps the two pieces of the same wave function. Bizarre as it may sound, two parts of the same electron come back and they interfere. It's strange, but quantum mechanics allows that, and that's what really happens. So this is an interesting thing, again, for the scientists in the audience. This is an interferometer. We're interfering two parts of the same electron. I'll tell you why it's interesting, and I think I'll understand it right away. I want to concentrate on that overlap part of the peaked wave function and the wave coming back. So the wave coming back, here's shown an overlap, and everybody knows about the interference of waves. If you go to a pool and you make two waves and you look at the end of the pool, you'll see ripples that interfere and so on, where the two waves either collide and add together or they don't, or they subtract from each other. And that's what's really shown here on these two images, how these two waves add together, the one that was fixed originally and the one that's coming back and recolliding. And, well, that wave and that interference leads to an oscillating charge, and that oscillating charge is what gives the light out. So what I want to say is this is a beautiful way to look at or to make charge oscillate around in a molecule. And it's that oscillation around in the molecule that gives the light. Or you could say the light measures the oscillation in the molecule. If the light measures the oscillation in the molecule, the light is measuring the size of the molecule or the size of the atom. So maybe we can measure the size of an atom. The electron is on the wavelength of the size of the atom. I illustrate that right here. I illustrate it by diffraction because you may all have experience with diffraction. Through this electron coming back and recolliding, you can see the structure of matter, angstrom structure of matter. Shown here in the image is the electron coming back, just like you saw before, the plane wave coming back. There are two rocks in the water, if you want to think of it, two atoms of a molecule, if you wish to think of it, is what it really means. And it scatters off these two atoms, and you get all the ripples and the interferences like you'd see at the end of a pool. So that means that the same process will allow us to measure time and space. Time and space. I want to end up by talking about one of the most interesting experiments we did. So again, I would like to bring this out in the open because many people like to read about quantum mechanics and think about it and all those bizarre things about quantum mechanics. Some people say that there are things that are unmeasurable in quantum mechanics. For example, an orbital that holds together a nitrogen molecule, for example. Some people might think this is an unmeasurable quantity. Some people think that even a wave function can't be measured. And I want to give you now give you an idea, I can't tell you about the experiment very much, about how to measure it before I stop, how to measure or how to get something that looks quite a lot like an orbital. So everybody knows about tomography. Everybody knows, because I should have put maybe a picture of a tomography, but everybody knows about tomography. Go to a hospital, they put you in a machine, and they take pictures of you from every different direction, and by taking pictures from every different direction, you can reconstruct the structure of your body. See your organs, see everything inside in full 3 dimensions. So can we make the same kind of measurement on a molecule, on an orbital, on the electron that holds a molecule together? This is an artist illustration, but I thought it was the best way to show it. So shown in the things with the plus and minus on it is what we think of, what we know, as a matter of fact, I don't mean we think of, as the orbital structure of the bonding electron in nitrogen, the most weakly bound, the one that's responsible for a lot of chemistry. So you can see the pluses and minuses, and that simply means that that bonding electron is moving back and forth, and like a wave, because it's always a wave, it sort of has 3 ripples in that wave. That's really what that orbital means to look at. And my question is, can we now do tomographic imaging on that molecule? And the illustration has the electron coming back and recolliding and taking a one-dimensional projection of the molecule. And what we're going to do in the experiment is rotate that molecule in many different angles, from parallel, as I showed you there, to 5 degrees, 10 degrees, 15 degrees, 20 degrees, just like a tomographic image that you would get in a hospital. I can't show you the experiment because I would take another half hour, and I'm sure Mr. President would be very disturbed with me if I did. So I'm only going to show you the results, and then I'm going to quickly finish. So I'm going to show you a 19 angular projection of the orbital of a nitrogen molecule. On the top you see the experiment, so that's the measurement we made. We're using tomography, the same algorithms that a hospital would use. We see the oscillation, effectively, of the electron holding the molecule together. It's color-coded in the red, blue, and red in the upper figure. And the one to look at, to compare it, is the bottom one, which is a calculation, the best calculation that you can do of the multi-electron calculation of an orbital filtered for the wavelength range that we have for the tomography. So Attosecond science allows very fast measurements and high spatial resolution. So let me just end then to say that I think personally that this is a really exciting area. It extends an old tradition. I said a century-old tradition of fast measurements. It's probably older. First movies were taken about 150 years ago, and of course, man has been interested in measuring fast things forever. And it brings it up to the time scale of the electron, a very important kind of measurement. We expend a 50-year-old tradition of what happens when you shine bright light on things. It's called nonlinear optics, no different than hitting the piano key too hard and hearing the not so beautiful sounds of the piano when you hit too hard. And it opens up new measurement methods like tomography. I just discussed it. We build on a 100-year-old tradition of X-ray science, and I think we're well on our way to integrating X-ray science with laser science. And finally, I think we're beginning to influence, maybe not yet in a big way, but they're influencing us in a big way, the 100-year-old tradition of collision physics. And in this case, we're trying to integrate space and time, measurements on attosecond and time and angstrom, time and space. So I want to end with 2 images. I have an image taken in front of the laboratory. The laboratories are the National Research Council laboratories. You see them up in the upper left. And so a number of people here have visited right across the street because Canada's external affairs is right across the street. This is a beautiful location for a laboratory right on the Ottawa River. And the building you see on its left is the home of the first Prime Minister of Canada. Those who are very, very vigilant will realize that it's a scaled model of Buckingham Palace, 1/4 scale. So the National Research Council is like Buckingham Palace. And on the bottom left are the people who are working in the group right now, people who are contributed to this work. I can't name them all, of course. But I wanted to go back and pick up an older photograph. And so here's one from 2007. And if you look carefully in this figure, you will pick out one person in the audience, actually one person from the Technion. Avner Fleischer is in the picture. And if I had picked out pictures from other times, there were a few other people who will be sitting down there that were in the pictures as well. So I would like to thank everybody very much. I'm very, very pleased and excited to get this award. Thank you.